Just some housekeeping in the chat. Margaret put a link if you do need credit. This is an accredited program. There's a link to a Google Doc that you can fill out. And any questions can be entered into the chat as well. Okay, I'm going to get started just to be respectful of people's time. I think we'll have other people filter in. But just wanted to welcome everyone. My name is Justin Giovannitti. I am co-chair for BEC Baltimore. BEC Baltimore is affiliated with AIA Baltimore and the National Institute of Building Sciences. So we were chartered about 6-7 years ago. And there are a number of BEC Building Enclosure Council chapters around the country, probably around 40 now, I would say. So our kind of mission is to bring about discussion around building enclosure related topics, anything from performance, durability, sustainability, kind of cutting edge technologies, anything that is enclosure related we'll talk about. Now we, unfortunately, because of kind of circumstances around the COVID pandemic, we haven't been able to host regular meetings as we have previously. So this is actually our first meeting in about a year, and welcoming some familiar faces and some new faces. So we appreciate that you joined us today, and I think everyone will enjoy this discussion with David. It's a little bit different. We are, kind of focusing in around virus transmission and steps that can be taken from an MEP standpoint to kind of mitigate that transmission. But I think it's really topical. As I mentioned before, if you have questions, just put them in the chat and we'll get to those. In terms of future events, so on May 18th, we're going to be hosting our next BEC Baltimore event. And we're going to be looking at building enclosure test chamber demo. So it's going to be kind of a virtual hands-on thing. So it'll be a Zoom, but we'll see an actual test chamber and get to learn kind of what enclosure tests are possible and how they get executed. So I think that'll be a good one as well. So you'll see, if you are on our mailing list, you'll receive a link for sign up for that shortly. Again, that's May 18th. It's going to be at 12 p.m. If you're not on our mailing list, I suggest just going to our website, which is bec-baltimore.org. And right on the homepage, there's a little form to put in your email and name, and you'll be brought up to speed on our future events. So we try to have 4 to 5 events per year. And right now they're going to be virtual, and hopefully later on this year we can get together in person. That's to be seen. So for now, I'm going to turn it over to Michael, who's on the board of BEC Baltimore as well, to introduce our speaker.
Thank you very much, Justin. I'd like to share with you some background prior to the presentation. David Vandervalls is Senior Vice President of Allen & Sheriff. Dave brings a vast array of design experience to his projects. During his tenure with the company, Dave's role has evolved from the entry-level position as a drafter in 1993 to his current Senior VP role, where he's responsible for overseeing company operations. In his corporate role, Dave works closely to assist with corporate business functions and with individual office leadership to ensure implementation of quality control measures, client service, profitability, and team training. His business and broad engineering background brings a unique skill set to the company, and he upholds the firm's commitment to community engagement through not only providing direct design support to many local nonprofits, but also by actively participating in local organizations such as the Greater Salisbury Committee, Salisbury Environmental Task Force, Boy Scouts of America, and ACE Mentoring. Most recently, Dave oversaw the firm's COVID-19 research, education, and response, providing free seminars to over 60 groups and 800 individuals on aerosol transmission of COVID-19 and how to reduce it using HVAC systems. He's currently focusing on opening the firm's newest office which is located in Wilmington, North Carolina. And with that, I'd like to introduce you to David Vandervoort.
Thanks a lot, Mike. So yeah, this is our AIA seminar. It's Actionable Steps using MEP to reduce transmission rates. We'll stop after each section, see if anyone's got any questions, or you can pop them in chat. So if Bill or someone else can monitor the chat a little bit, I don't have it up on my screen here because I'm looking at the presentation that we're sharing. But we'll go through, and I guess a couple of things we would go over is, I mean, there's been less focus on some of this stuff recently as people are seeing the virus start to come down a little bit and things like that. But where we've seen the benefit and beyond, reducing transmission rates is making our employees, beyond making it public, but making our employees comfortable to come back to work and things like that. We think architectural engineering is more of a contact sport. You kind of need to be in person communicating and, coming up with ideas together. And so this helps get your team back in the building or your client's teams back in the building. We've been back in our office since late April, early of May. All 4 of our offices have been in because we implemented a bunch of these steps, and our guys are up to speed and understand how this benefits them and how it works. So anyway, with that, we'll get going through here. So there's our standard AIA blurb. And then we'll read the course description, acknowledging that COVID-19 is primarily transmitted as an airborne virus. The course will review how can MEP design help reduce those risks. We provide a base understanding of how we catch viruses, including COVID-19, review actionable items for reopening and long-term strategies for pathogen control. At the end of this course, participants will be able to understand the 3 primary transmission methods of COVID-19 and typical preventative measures, understand infectious dose and viral load, short-term HVAC approaches to reduce transmission to include ventilation, filtration, long-term solutions for pathogen control, including air sanitization, and what other MEP design items we can do for pathogen control. So first, we want to hit a little side note. So if you still have a building that either a portion of the building's been empty, or you have clients that either a portion of the whole building's been empty for an extended period of time, anytime the building's been empty for more than a week, or a portion of the building's been empty for more than a week, you need to flush out the lines. This link here, and we'll provide the group a PDF of this whole presentation. This link here gives you instructions on how to flush out the lines. If you're uncertain how long to run them, run them longer. It's a little bit of water we're using. So Legionella is by far the most common waterborne bacteria we have here in the U.S., and we have seen an uptick in Legionella cases. So basically, it grows at ambient temperatures. The chlorine wears off after about a week in the system. So then the Legionella can start growing in our water lines. So that's where the risk is there. So that's kind of a side note. Make sure your buildings, and look out for ice maker lines, coffee maker lines, little longer runs like that are smaller, that don't get as much flow. So we have 3 transmission methods. Fomite is touching the surfaces. So you cough on your hand, touch a doorknob, the next person comes through. Droplets is close contact, person to person. And then aerosols is when those droplets go longer distances. And it's important that we address each transmission method. So fomite, again, that's touching the surfaces. And that's where you guys as architects have got into material selection, things like that, hand washing stations and all. It was back in May 22nd, the CDC basically came out and said this isn't thought to be the main way the virus spreads. So if your main approach to COVID-19 is hand sanitizer and cleaning everything, you're if that's your biggest effort, you're missing the boat. So make sure you look at the other 2. That's important, but it's, again, not the main way it spreads. So we have 2 charts over here on the right-hand side, how long COVID-19 lives on common surfaces. And then you'll see up there, it stays in the air up to 3 hours. So that's be important as we get into the aerosol discussion. And then because it's not always going to be COVID-19, these are other pathogens and how long they live on surfaces. And you can see Salmonella, for example, lives up to 4 years on surfaces. So that's fomite. And again, we need to make sure we address all 3 transmission methods. So you got to do what the steps for this. And the second one is droplets, and this is thought to be the main way. And this is why you have the 6-foot spacing, the masks, the screens, all that. And that's where you guys got into doing, single directional travel layouts, orientation of desk, room limits and stuff like that. We saw a lot of architectural responses on different from different firms doing those sort of things. And then this is a SARS virus study that was done years ago, which still applies today. There's been a couple other studies that have slightly different numbers on distances, but you can see how far the large and small droplets carry. And then when we get into what's called droplet nuclei, how far they carry, so up to 160 feet. So when we talk about droplet nuclei, basically it's droplet nuclei, aerosols, virins, micro droplets, different papers, different groups call it different things. It's all the same stuff. So what's basically happening, and I guess we'll go into this part first. So this was kind of a side note and not really being addressed by the WHO, the CDC, and everybody else up through the middle of the summer when the WHO received a letter from 238 researchers that said, okay, guys, this is clearly an issue. It's what's causing some of the super spreader events. You need to bring this to the forefront and stop downplaying this part of the issue. So until then, again, this is a very side note. You can find little notes on it in some of the case studies in the CDC. ASHRAE was all over this ahead of time, but the CDC and WHO kind of really downplayed it. We've actually been talking about this, we've been doing this presentation since end of April last year. So it was clearly a thing ahead of that. It just, was on the down low. So basically what's happening is if you're sitting at your desk and you happen to be a carrier and you're just sitting there working, you're going to expel virus particles as you're breathing. And it's usually about 30 to 35 virus particles a minute. And they're going to come out as large droplets and small droplets. And they're going to, basically the viruses being encapsulated by water and mucus. And as it carries through the air, it's going to start to evaporate. And if it comes into contact with the surface before it evaporates entirely, it'll stay on that surface. If it evaporates entirely, before it comes in contact with the surface, then those virus particles are going to stay airborne. They're basically at that point the same weight as the air, and they're just going to start carrying around in the air. So that's how they carry to that 160 feet. So that study, basically they studied an area that was 160 feet. So that's how far they carried, but they'll go through whatever volume of space that they're in and keep carrying through. So again, that's the key part, is if they come in contact with the surface while they're still, have water and mucus on them because that weight pulls them down, then they'll stay on that surface. If they evaporate before that, then they'll stay airborne. And so that's what we're really looking at. And as you're just breathing, it's around 30 some odd particles a minute. If you talk or sing, and the more you do, the more virus particles come out. If you cough, it's a couple 100,000. If you sneeze, it's a couple 100 million virus particles. So there are quite a lot that can come out. But really what we need to look at is we need to become familiar with what's called infectious dose or viral load. So if I'm walking through the park, someone's going the other way and they happen to have the virus, and unless they cough or sneeze directly on me, I'm not going to catch the virus from them. I'm not going to, even if they push out 100 virus particles my direction, I bring all 100 of them in, I'm not going to catch the virus. The infectious dose level is how many virus particles I need to get to catch the virus. There's not been a study put out that I've seen, but there's been studies looking at the infectivity rates of other viruses and versus this one, and what the infectious dose level was of the other viruses. So the best numbers, the most common numbers that we see tend to be around 1,000 particles. So, basically saying you need to reach 1,000, you need to bring in 1,000 particles of the virus for you to catch the virus. The other concept is called viral load. So viral load is how much you bring in and how severe of a case of the virus you're going to get. So this applies basically to all viruses. The more the virus particles you bring in, the more severe case. So if your infectious dose level is 1,000 and you bring in 1,000 particles, okay, you're going to get likely to get COVID-19, but it's going to be a very minor case. If you get 100,000 or 10,000 particles, you're going to get a much more severe case. The more you bring in, the more you're going to get. So then what we're looking at is really the exposure duration, how long we're being exposed to a room that's got virus particles in it, and the density of those virus particles in the space, because that's going to determine how many virus particles we bring into our bodies. So that's kind of what we need to look at in terms of a math level. So there's two case studies we're going to look at. The first is a Washington State choir practice. So this is all the way back in March of 2020. We had one carrier. It was a 2.5-hour practice. and we ended up with 52 new cases. And the CDC looked at it, and they're basically, it's not fomite because there's not enough physical contact. There's not droplets because there's no way that they got close enough to each other over this time. So it was really a aerosol version is what they were looking at. And again, because the carrier was singing, they're expelling more virus particles. And because everyone else is singing, they're bringing in a lot more air. So they're increasing the amount of particles that they're bringing in. So that's kind of what happened here. The other case study is a South Korean call center. And basically, it's all these blue seats that we're looking at. So we had 811 employees over 3 floors of a 19-story building. And there was 97 cases, 94 are on that same floor, and most of them are all on that same side of the building. So what you're looking at was it's not going up and down the elevator with a person. It's not interacting in the hallway for a second. It's staying in that same area with that same HVAC system, circulating the same air for an extended period of time. So over a day or two, whether they're bringing in 100 or 200 virus particles an hour, these other people in this space basically got the virus that way. The other 3 cases that were not on this floor, they were not determined exactly how they got it or where they got it. So they could have been from this carrier or it could have been from someone else entirely. And what's included here was it was the duration of the interaction that was likely the main factor. So again, so we had 2 case studies from aerosols back in March of last year. So what are we trying to do from an engineering standpoint? So we're trying to reduce the number of virus particles in space and reduce the exposure below the infectious dose level. So if we can bring down the density of the virus particles in there, hopefully we get everyone below the infectious dose level. And if we don't get everyone down, maybe we reduce the number of people that get to the infectious dose level, and we will definitely reduce the viral load that they bring in. So if we reduce the virus particles in space by half, then everyone gets a half the viral load that they had before. So any bit we do helps out the number of cases and the severity of the cases. So we have 3 main actionable steps that we're going to do that are recommended. The first is increase our ventilation or outdoor air. The second is the filtration. And the third gets into air sanitization. So we have a typical commercial system that we're going to use as our example project. So this could be a 20-story office building that has an air handler per floor. The numbers and the systems are going to run very similar. Or in this case, we've got a little rooftop unit on whether it's a school or an office or a retail space, doesn't really matter. Most of the time we're going to have a 15% exhaust or outdoor air rate. And most of our smaller equipment is going to start around MERV 8. Some of our larger equipment might have a slightly higher filter level. But if we apply these standard numbers to most of our buildings, this is kind of our common starting point. So what we're going to have here is with the 15% outdoor air, we're going to be exhausting 15% of the virus particles every time it goes through the system. And then we're going to capture another 11% of the virus particles. And we'll get a little more into how that, where that number comes from. So if we do that math, we take 85% of the particles and then multiply it by the 11% that's going to be captured from there. We end up with a 75.6% pass-through rate. So basically 3/4 of virus particles are making it through the system, 1/4 is being pulled out. And we're going to typically, most of our spaces, we're going to take this whole volume of air in the space and push it through our units, typically about 4 to 6 times an hour. So 4 to 6 times an hour, we're pulling out roughly 1/4 of the virus particles. So our carrier is, if we happen to have our carrier in here, they're going to be adding virus particles. So we want to be trying to pull out virus particles at a quicker rate than they're adding them in. So this is going to kind of be our starting point, and we're going to start putting our steps and looking to see how it affects our system. So if we look at what happened here, sorry, it jumped a couple slides on me there. So we have demand control ventilation. Most of our outdoor air systems on our current buildings and larger buildings, just about everything now is required by code to have demand control ventilation, which typically we do with CO2 sensors. So it's going to look at the CO2 levels in the space. That's going to be correlated with how much people are in the space, and then we're going to ramp down our outdoor air based on that CO2 sensor. So if we have a space that under design conditions is supposed to be 15% outdoor air, but the CO2 sensor is telling our system there's only roughly half the number of people in there, then it's going to be running at about 7.5%. So that's energy control requirement that we have in there. So the first step we're going to do is we're going to turn off those CO2 controllers during the pandemic. So the last thing we want to do is have our system be told to throttle back that outdoor air because we don't have as many people in the space. We want to maximize the outdoor air. So again, the first step is turn off that CO2 controller, and we go straight to an occupancy schedule. So hey, the building becomes occupied at 8 o'clock. We open out the outdoor air to our set point, 15% in this case, and then we keep it running throughout, so that we're not saying, oh, well, there's only a couple people in here, let's reduce it down. We don't want to do that. We're going to go turn off the CO2 controllers, go straight to a schedule. After the pandemic's over, we believe that the CO2 set points right now, we're typically running somewhere between 800 to 1200 parts per million is typically our set point we're trying to control to. We're likely going to, over the long run, start to bring that down, which will push more outdoor air into our space. That could be after the pandemic's gone, the new standard will be those CO2 levels start coming down as to what we're setting for. The second thing we're going to do is we're going to increase the outdoor air level. So basically, if I can run 15% in our design condition, we're going to review the system capacity, and we're going to say, okay, at 80 degrees, we're going to calculate the capacity of the system. At 80 degrees, maybe I can go to 30 or 35% outdoor air. At 70 degrees, maybe I can go to 50. At 60, I can go to 100%. And so we're going to figure out a schedule of, at different temperatures, how much outdoor air we can run. And the same thing on the winter, how far down, as the temperature goes down, how much outdoor air I can bring in. And what the ASHRAE and CDC say is we want to maximize that outdoor air level at all times throughout the day. So ideally, we want to monitor, have that ramping up and down as the temperature changes throughout the day. So on most of our buildings, anything that's a little larger with a little more control system, we can look at the discharge temperature of our system. And as long as, if we've got a design discharge temperature of 55 degrees, as long as our system can keep up, we're going to keep ramping that outdoor air up until it can no longer keep up with that air coming in, and then we bring it back down until it's under control. So that way, throughout the day, as the temperature climbs, that outdoor air is going to be maximized, and it's going to adjust according to what the capacity of the system. So we're always going to get as much outdoor air into the building as possible. If we don't have that level of control, we have a smaller building, we have a 10-ton rooftop, it has a little less. There's two options here. We can have a schedule where we've calculated it, and we can say, okay, today, at this particular time, our outdoor temperature sensor says it's 80 degrees. Our schedule says at 80 degrees, I can handle 30% outdoor air. And so we have the damper go to that. If we don't have that level, we can just manually, one of our offices, we actually were doing this. We would look at the temperature, predicted temperature for the day, and we would just manually go in there and say, okay, it's going to be 80 degrees today at the peak temperature. So we're going to set our outdoor air to 30% because that's what we can handle an 80-degree day. Ideally, we get to a discharge temperature control because with partial occupancy or everything that's running, we may be able to do more than what we calculated. Calculated versus actual capacity can be different sometimes. So we always want to push it as far as we can. And the third step is going to be running longer occupied times. And this is one of the things that's changed a lot over the recommendation period. So originally, the CDC was saying run 24/7. They've reduced their recommendation now to 2 hours prior, 2 hours after. And then ASHRAE started off with saying 2 hours prior, 2 hours after. And now they've gone to where they basically want you to flush the space with the whole volume of space 3 times with that much outdoor air, which depending on how much outdoor air you're running can be 1 hour, can be 3 or 4 hours. So you have to do a little math there. But originally they were saying 2 hours. So for argument's sake, we're going to say 2 hours prior, 2 hours after. So those are the 3 steps what we're going to do. Again, we're going to turn off the CO2 controllers so that we're not throttling down. We're going to push the outdoor air level as much as capacity as we have in our system. And then we're going to flush it out. We're going to run before and after the occupied period of time. When we get into talk about new system selection, we maybe start pushing some of our systems towards an air side economizer setup. Energy codes right now, anything over 2.5 tons basically require an economizer. So if I have a water side system, my free cooling is going to be coming through the water. So I typically am not able to push my outdoor air past 15 or 20%. So that doesn't give me the ability to push this up. It also doesn't give me the ability to flush the building if something were to happen in terms of I had an outbreak or something. If I have an airside system, I have a rooftop unit with an airside economizer. As the temperatures are better, I can do 100% outdoor air. My economizer mode goes to 100% outdoor air, so I can it's flushing the building. It's maximizing the outdoor air coming through the space. Or if I have an outbreak, I don't care what temperature it is, I can flush my building, and I don't care about the temperature at that point in time. So depending on your type of building and what your owners want to do, this could push our system selections moving forward. So if we take that and we run it on our particular example project, again, we say, okay, in this particular moment during the day, I can handle 30% outdoor air. I'm going to be exhausting roughly 30% of the particles. So now I'm going to take that 70% that was making it through, multiply it by this 11% effective filter, and we end up with a pass-through rate that drops down to 62.5%. So we went from 75.6 to 62.5. So now we're capturing a little over 13% additional virus particles, 13% additional particles. So we're starting to thin out that concentration. And again, this is going to happen 4 to 6 times an hour. Now, if I can say it's 70 degrees or whatever, and I can run this up to 50%, that's going to bring this pass-through rate, I think it gets it down to like 42% coming through. So, if we can push this, that's why you want to push this as maximum as you can throughout the day. So earlier in the morning, maybe it was only 70 degrees, I would be running 50%, I'd have a lot lower pass-through rate. But this particular time, we end up with a 62.5%. So that's kind of, first step we have going. And this is something we think all our buildings can do to some extent. So there's a first step, and this is why it's recommended. You just need to figure out the capacity of your system and kind of figure out where you can go with it. Every 1,000 CFM of outdoor air we have adds about 5 tons of cooling to our load. So this is capacity limited. You can't just keep cranking it up and run 100% outdoor air all day. Obviously, your system's not going to keep up, and you're going to lose control of your temperature and humidity. So you have to look at the existing capacity. If you're designing a new system, are you going to increase the capacity? We would argue that there's other solutions that we could look at that avoid you doing that. So we'd probably stay away from that. If you're in the DC market, you have to report your energy usage every year. So this is going to impact your Energy Star rating and your reporting on that. If you had to do a lead reporting, keeps jumping on me. If you had to do lead reporting, for your 12-month report, you're going to use more energy than your model had stated. So you're going to have to explain that, what happened there. When we look at outdoor air coming to our building, so we have, if I bring outdoor air and it goes to my central air handler, if I have a VAV system, I'm going to have VAV boxes or some sort of dampers that throttle back that system. Once I get control, once my temperature reaches the set point in a space, we're going to throttle that box back, and I'm going to reduce that air to that space. So we have to look at control strategies that'll keep pushing that out there to the space. If we have the air handler but never gets to the space, we haven't really done anything. So we either have to lower the set point, the discharge temperatures, so maybe bring them down from 55 to, or increase them rather from 55 to 60, so that box will stay open longer. Or we look at saying, okay, my minimum setback on the box is going to be 15%. Maybe I push it up to 20 or 25, so it runs outdoor air a little bit longer into the space. Both can impact the capacity or the temperature in the space. So there are some trade-offs here.
Hey, Dave.
Yes, sir.
Hey, there's a question here. Going back to the CO2 monitoring.
Okay.
Is measuring CO2 alone enough to determine the quality of the indoor air?
So it's the CO2 is actually, there's studies out there that show the CO2 is actually not all that harmful to you, but it's what's the right word I'm looking for? It's basically a representative of the composition of the air and the other contaminants of concern is what they call it. And there's a list of about 30 contaminants of concern that you're actually trying to handle. But it is the most common way to look at the contaminants in the air because it's representative of how much other contaminants are in the air. Typically outside, we're around 400 parts per million, and inside we get up to 1,000 or so is our kind of a typical control point. But David, we do have.
Can I ask something else about that?
Yeah.
Does it matter where you measure it? So if you're measuring it, say, in the space versus in a return duct?
It won't matter. It's not going to matter a whole lot. You kind of typically will put it in the return. There are requirements depending on, how many people are in the space, how many dense spaces you have that you have to monitor. If you have multiple conference rooms, you're supposed to monitor each conference room, things like that. There's some places where you can, kind of a mixed use office or whatever. Some of them you can just do one sensor. Others, if you're likely to have multiple spaces that are going to vary in occupancy, you're supposed to monitor each different space, which then could push, and then you treat the worst case one, which then you're over ventilating other spaces. But that's so you don't under ventilate the first one. But CO2 is the most common way to monitor the condition the indoor air. Does that answer the question, I guess?
Yep.
Yes. Okay. When we get into bipolar ionization, we'll talk about that a little bit more about the contaminants of concern, because there's other stuff you can do with the bipolar ionization that can help out some. Operable windows. So we've talked to schools about this in particular. There's a lot of schools, especially the older buildings, that don't have as elaborate systems, where they'll have operable windows, but a lot of them have been fixed in place over the years, either because they're just maintenance issues or because of security reasons. They want to fix them in place so people can't get in the buildings or whatever. So we've encouraged them to go back and figure out how to get them working again. And it's a very effective means of bringing ventilation into the space. It's not as consistent, but it can bring quite a bit of area in to the different spaces. So anytime you can do that is good. The hospitals, I don't know if everyone remembers back, China built these hospitals in 10 days. They were these modular things, but they were all based off of natural ventilation. So they all had operable, they were very narrow buildings, and they had operable windows on both sides and things like that. Questions on ventilation? Is there any other chat? Where I get to the chat. All right, that's the only question I see there. Anybody else have any other questions on the ventilation? All right, so we'll jump to filtration. So we started off with the ventilation where we were diluting the air basically. With filtration, we're going to try and filter out the contaminants. Again, we're starting point we're looking at our typical MERV 8 filters. We're going to review our systems. We're going to look at the static capacity of our system. So basically, we're going to look at how big is the unit, how big is the fan, how much air can it push, and how much resistance can it deal with, how much ductwork is already on that system. Our larger systems are going to be easier to do this with. Our smaller systems are going to be harder. Basically, as we push our MERV rating up, there's more resistance across that filter, which is going to increase the static. It's going to eat up some horsepower and some energy. So our smaller systems aren't really set up to they don't have as much cushion. Our larger systems do. ASHRAE and CDC both recommended out of the gate basically a MERV 13, and we'll get into why here in a second. They also made some interesting recommendations. ASHRAE's also updated their school recommendation to MERV 14. But the MERV 13, the way they stated was this is kind of your goal, but if you can go farther, go farther. If you can't get there, go as far as you can. And they both say very similar statements along those lines. So the reason they want you to go to MERV 13 is, so this is a swine flu study. And there's another chart with a bunch of curves on it that shows essentially the same numbers. And the swine flu and the COVID-19 are both about the same size at 0.125 nanometers. So the charts are very similar in their effectiveness, or essentially the same. So a MERV 8 captures 11% of the virus particles, but if you can push down to a MERV 13, you're going to capture about 46% of the virus particles. So you're over 4 times the number of virus particles you're picking up. And if you can get to 14, it's in the mid 60s, and then 15, only picks up a little bit more. So this 13 jump and then the 14 jump are pretty significant. And you do have filters that go all the way from a 1 to a 20, a spun fiberglass type deal that you might have at your house, or a washable filter is around a MERV 4. Pleated started at about a MERV 6. And then, like I said, most of our commercial stuff starts around a MERV 8. When we get into the higher level filters, people ask us about like a HEPA filter. Why don't I just put a HEPA filter in? Well, the reality is even hospitals, they don't use HEPA filters throughout. So they'll reserve them for lab spaces, ICU spaces, surgery areas, things like that. Most of the rest of the building is going to be using a MERV 15 typically. The resistance across the HEPA filter is very extreme. They're very large. You have to replace them frequently. So the cost associated with this is, most of our systems can't handle that resistance to start with, and then the cost is very high. So typically we're going to cap out around a MERV 15 on anything we're going to do on a commercial standpoint. So if we put this in effect on our building, we kind of do our, leave our first step in of our outdoor air. So on this particular day, we're running 30% outdoor air. So again, we're exhausting 30%. So we have about 70% of the virus particles making it past that step. And then we get 46% of those that we're going to capture. We bring this down to a 38% pass-through rate. So with those two steps, we went from 75.6 down to 38% pass-through rate. So we're capturing like 2.5 times the number of virus particles. And again, that happens 4 to 6 times an hour. We're pushing this whole volume of air through our unit, and we're going to capture 62% of virus particles each time. So now you can see we're really starting to thin out the number of virus particles in here. Again, our carrier is still adding to the space, but we're really thinning this down. So with those two steps, that again, we would argue virtually every building, every system, we can do some version or some portion of this. We can really reduce the number of virus particles in our spaces if we have a carrier in our space. I mean, obviously the first thing is get the carriers out of the space, but if we do have someone coming in, we're going to really thin down these particles. So, we would push that every building should be looking at this, figure out how big of a filter you can get, and figure out how much outdoor air you can be running, and do these things, and we can really make a big difference. So again, our goal is kind of a MERV 13. Our filter costs are going from a MERV 8 to MERV 13 are going to be roughly double, and we're going to have to change them more frequently. Our recommendation is once you start using MERV 13s, check them once a month. We're not recommending you replace them once a month. Replacing a filter before it's loaded up you're just spending money for the most part. So you want to look and figure out what your new frequency is going to be. If your frequency was every 6 months before, maybe it drops to every 2 or 3 months. So you're going to have to do it more often, and the filters are more expensive. Again, our larger units are going to work a little easier. So our central station air handlers, we're going to be able to get to 13 or 14. Our VAVs, we're going to have a little more on that, a little smaller filter on that, and the smaller equipment. If VRFs and things like that, we're going to have a hard time pushing these filters up. If we're doing new equipment, most smaller equipment now, because LEED's been pushing this push for MERV 13 probably for 6 years or so, you can buy newer equipment, smaller stuff with a MERV 13. Not all manufacturers, but it is available out there. So the other thing to look at is each filter manufacturer and the cost per those filters. So we were working on a building in DC for a law firm, and we were looking at their air handlers that the landlord was using, and they had a MERV 13 filter. It was about $140. It had a steel case around it, and it's a pretty nice system. Their MERV 14 filter from that same manufacturer was being $140 was $141. So it was $1 more, and they went from a 46% filter to it was mid 60s somewhere for that $1, and the pressure drop was almost nil. So we made that recommendation to them. So every manufacturer in each case is going to be a little different. So you really need to look into it to see how far you can push it. That one step really made a difference there. Leakage or bypass is a big issue. So if I have a MERV 13 rack that I put in, this happens to be one of our offices here, and we have a 10-ton rooftop serving this building. It's a 3,500 square foot space. We have a 10-ton unit serving it. We have MERV 13 filters in there that we put in. If I had a 1/2-inch air gap in there, it would derate the system down to basically a MERV 8. So what we've done here, what they work is very simple, very cheap. We basically use this blue painter's tape. So as we slide the filters in, you tape one filter to the next filter, and you keep sliding them in. And then at the end of the rack, we tape that gap too, because there's about a 1/2-inch gap there. And so we eliminate any chance of bypass between the filters around the end, at least on the accessible side. We can't really get to the other side there. Some filters are going to have spring clips or gaskets or something like that. Make sure all that stuff's very serviceable and it's in good shape. You know, if half the air is going past the filter, not going through it, obviously it's not going to be capturing things. Portable fan filter units. So this comes up, you know, whether you want to buy the little room size one sitting there, or, you know, this picture here happens to be like a lobby or reception space. This is a bigger kind of one done for remediation. You can get these, they'll do about 500 CFM or so, but they're about 60 some odd decibels, and they'll have a HEPA filter in them, which will capture, you know, that 500 CFM going through everything in there. But when we look at comparing that unit there, where'd my cursor go? Comparing this unit here to our central system, if we were to take that same space and we put one of these in there and it's doing 500 CFM and it's capturing virtually all the virus particles, then I compare it versus, okay, I upgraded my central system and I put more of 13s in them and it's going to capture roughly half. So for that 4,000 CFM, I'm going to capture 4 times the number of virus particles that I am with this HEPA filter in there, and I'm not going to have the noise issue that I have going. So we're going to recommend to you that you always go to your central system first, go as far as you can there, and then look at, you know, other problem areas, and maybe you do portable units in those problem areas. We've also seen them if you've got perimeter fan coils or something like that that don't have the capacity to really push up the filters, then people might get the portable units for in those spaces. But wherever you can do the central equipment first, start there and then go on from that point. I would also push that, you know, if you go to get room sized filter units or whatever, you know, air sanitization, look at see how much of the air is going through the filter itself. Dyson, for example, has, you know, the circles or the ovals, and they're inducing the airflow through there. So they'll give you a rated CFM, but it's only about 1/10 of that air that actually goes through the HEPA filter. So you want to be doing, if you're doing those sort of room units, you want two air changes there. So you need to figure out the whole volume of the room and then convert it into CFM for cubic feet per minute to figure out you want to flush that room twice over. And so you probably want to stay away from like a Dyson style and go to one that pushes all the air through the filter. And I would recommend you probably want to pick it around the medium fan speed, so because it brings the decibels down to 30 or 40 or so. If you run it that high at 60, it's really distracting. It's not really a livable scenario long-term for people to be working in. Costs, when we talk about those 2 first steps, and then we'll see if anyone's got any questions here. So in our DC market, it's closest market from Baltimore, you know, Energy Star back, I think this was in September, I think it was, had Servodyne, who happens to be one of their most preferred vendor, I think, status I think they have. They paid Servodyne or had Servodyne do this study for them. Sorry, it keeps jumping on me. They went 2 hours prior and 2 hours after, and they did, because you had to pick them out of outdoor air, they did 50% additional outdoor air. And that cost worked out to 6 cents overall, 6 cents a square foot per year, additional cost. So there is a little bit of cost here, but typically most of our spaces, we're talking a couple $100, you know, maybe a couple thousand on our larger spaces that we're talking about over the year. We do think that the extended hours, you know, after COVID-19 kind of works out in the summer or fall, that the extended hours issue will start to drop. It will not really be the norm. The MERV 13s, we do think will be the norm. And we think that, you know, there was a code change in 06. We think the outdoor air will go up from where it's at prior to COVID, but not as far as it is now. There was a code change in 06 that reduced outdoor air mainly because of energy push. And, you know, ASHRAE's had a working group on this issue, and we believe that there'll be an update, which typically does get eventually adopted by IMC. But again, that's kind of the cost we're looking at running this stuff, not counting the filters and things like the cost of the filters themselves. So questions on filtration? We have any chat issues, or where's the chat?
Nothing in the chat, Dave.
Okay. Anybody else have any questions on filters, or we'll go on to the next slide here. All right, so UVGI, so air sanitization. So the most common one that we're going to look at is going to be, the most widely accepted is going to be UVGI. And our goal with any air sanitization is to mostly actively kill the pathogens in an airstream. And there's going to be two that we're going to typically use. And we'll talk about some other options out there and why we typically are not going that route with them. And UVGI is basically ultraviolet germicidal irradiation. So we're basically taking and we're exposing the virus particles or whatever pathogens to UV light to try and inactivate them. And we have two types of systems we're going to look at. One's an upper room, and the other one's kind of in unit or in duct. And the reason that we go with the UVGI is it's been around from 1910 for water and the 1940s and 50s for on the air side. So it's been out there a long time, and it's got a couple double-blind studies. So they've taken multiple floors of a building, put it on one floor and not on the other floor. And the floor that had it, people had notable better health outcomes, and they didn't grow a third arm or any other, negative issues. And basically the problem with the other studies, the other systems, so here's the other technologies that are out there, they don't have that same double-blind study. Basically what they typically do is they'll take a room, 10 by 10 room, put in, mold A, bacteria B, virus C, different pathogens, and they'll test that and run the system for an hour, and after an hour or 30 minutes, whatever it might be, they've reduced it from this concentration to this concentration. So basically these are all termed emerging technologies, and what ASHRAE and CDC both say on most of this stuff is that not that it doesn't work, it's just that it doesn't have the studies to show that there's not negative health outcomes because of it. So for the UVGI, again, we're going to take a 254 nanometer spectrum light, which is a UVC. It's a low pressure mercury lamp. It puts out most of its energy at that point. You'll see over here at 296 and 313 puts out a little energy there too. But most of it comes out of this 254, which this curve here happens to be the peak effectiveness of UV against different pathogens. And so the peak is at 265. This is the most common lamp we can get that's close to that peak. And it's just going to break down in either the DNA or in our case, it's an RNA for COVID-19. It's going to break down this ladder rung and keep it from reproducing, which makes it inert. So that's kind of how this works. We don't have a major health issues with with UVC. UVA and UVB is where we get our skin cancer and sunburns and stuff. UVC dies off at the upper level of dead skin cells, so that doesn't happen. We do have to watch eye exposure. You'll get welder's flash from it. So we have to protect the personnel from it, both the occupants and service personnel. Upper room, this picture over here happens to be a homeless shelter. If you've been in an emergency room, you've probably seen these. We would look at upper rooms in our larger volume spaces and our higher risk spaces, higher density, higher risk. So like emergency room, in case someone comes in there and they got TB or the flu or whatever it might be, you're going to treat that space as soon as possible. We do have to look at reflection issues. So we're going to put it 7 foot. It's going to have some louvers to keep it going up, but they've had issues where it'll bounce off a TV or a monitor or a sign or something like that. So you do have to look at that a little bit. And we can model this using visual to make sure that we've designed it to hit the right density. So this is kind of a limited application. We have looked at it at a couple locations. The fixture costs start off about $600 a piece and go up from there. So you're probably $1,000 to $2,000 per lamp installed, per fixture installed. And it's a lower intensity bulb because the air is moving slower. So I can get to that, the wattage that I want to treat each particle with by doing a lower intensity light because it's going to be exposed for a longer period of time. So my in-unit or in-duct, because the exposure period is a lot shorter, I have to do a lot higher wattage in there. It's still not that high. So if we go back to that same space, that 10-ton unit we were talking about before, one of our offices, we put in 3 lamps that were 84 watts, and we got what's called a single pass kill on that. So over 99% of the virus particles are killed off in that single pass through that system. So it's not a lot of wattage, but it is more intense than it would be in the upper room scenario. And it's because, you know, our velocity in our ductwork, is 1,000 to 3,000 feet per minute, and in our units about 500 feet per minute. So we have, you know, different velocities we have to size accordingly for. If we put it in the unit, we have to watch out for different soft materials. So, you know, if you think about plastic chairs and other things like that outside, the UV breaks down the, you know, soft materials. So our wires, our rubber gaskets, our insulation, things like that can't stand up to the UV. So we have to look, okay, can I put foil tape over the gaskets or foil tape over the wires? Can I move some of this out of that area? So you have to be careful of our smaller units in particular as to where you might put UV, and it's going to limit you. In some cases, you're not going to be able to put it in. In the ductwork, it's the same issue. You got to watch out for duct liners. So you either have to remove the duct liner for the sections that you're talking about, or you have to paint it or encapsulate it somehow. Any access panel has to have an interlocking switch to turn off that lamp so the service personnel don't open it and have that lamp exposing them. But what will happen here is basically every pass through here, we're going to kill off more than 99% of virus particles in our single pass. So what that's going to enable us to do is we're going to bring our outdoor air back down to our code levels. You know, before we were running 30% for our little example, we're going to drop that back down to the 15%. We could run it higher, but basically, you know, it kind of becomes a belt and suspenders scenario at that point. So we're going to bring that back down. So we're going to save that operating energy, and we're going to spend a little bit on the wattage on the lamps. We're going to recommend you keep the MERP 13 filters in there, basically for two reasons. One, it's going to capture all these dead virus particles that are coming through here. Another thing it's going to do, it's going to try and keep the dust off that lamp. The lamp's what's doing the work. You do need to clean these periodically. Most of the manufacturers are recommending just either a dry or wet microfiber towel. They don't want you typically to use a cleaner. Most of the cleaners will leave some sort of film on there. And again, the UV is very low penetrating. So that those films from the leftover from the cleaners can tend to block that UV. So now, you know, if you got someone go in there that cleans them that doesn't know what they're doing, all of a sudden you've made that lamp not work. Lamp life is about 9,000 to 12,000 hours, depending on manufacturer. So if you run it 24/7, you're looking year and a half that you're going to have to replace it. What we recommend is you run it whenever someone's in the space. So either an occupancy sensor, or we've tied some of ours on just to a time clock, or one of them's tied onto a light switch that's turned on anytime anyone's in the space anyway. Again, very low wattage, so we can just tie it onto a local circuit pretty easily. And that will stretch it to a little over 3 years, doing it that way. Again, we already talked about the cost for the upper room. In our air handlers, we're looking between 50 cents and $1 a square foot. We've had some lead time issues on some of these. They are out there 10 weeks or so. So getting some of the systems does take a while. We talked about the issues of retrofitting. It is a relatively low operating cost. The lamps do cost about $100 a pop. So you do want to try and get the most you can out of them. That's one of the reasons not to run it 24/7. You can get these portable units. They'll clean surfaces. So the hospitals have used them for a number of years. And they start off, the small ones start off around $6 grand for that. So we've had one hotel chain look at it, and we had a school system look at it. I'm not sure if either one of them did pick that up for treating some of their spaces or not. Questions on UVGI? Oh, something popped up in the chat or something. Fixtures, what determines spacing in the room? Well, the first one, ozone is not a concern for UV. It does become a concern for bipolar ionization, which we're going to talk about next. UV fixtures, if you go back, let's see here, close this chat. So they want you to get to this microwatts. I forgot what that Greek symbol is there, but so they want you to get to this density on the wattage. So, you know, that's each fixture is going to put out a certain amount of light. It's going to go a certain distance. The longer it goes, the less dense it's going to be, but it's still treating it. So if you only have a couple, you want to put it on the short walls rather, so it can travel the longest distances. But that's why we would use the visual, because basically it's going to have a pattern, like we get the IES files for lights and it shows you how much density the light is. Well, we're going to get the same thing. It's going to just be in terms of, you know, a different spectrum. So we're going to get those same files, and then we can see what the density is throughout that space to make sure we've got enough fixtures in there. The other way to look at this is if you can't quite get there, doing something, say you got a restaurant wants to do something because it's very visible, or a hotel lobby, but they only have $4,000. Well, putting a couple of them in are going to help. It might take longer, but it's definitely going to help. So that's kind of the trade-off, but there might be a better system for their limited dollars too. Any other questions on UV? All right. So needlepoint bipolar ionization. So the first thing here is, again, this is one of the emerging technologies, quote unquote, because it doesn't have the double-blind study. And I'm not really certain why none of these manufacturers have pushed for this. This has been around since the late 80s or early 90s. We do have several hospitals we've worked with that have had it in their different systems. So we're fairly comfortable using it based upon that information. And basically what you're looking at here is this is bipolar ionization, and it's the needlepoint is what you want to use. Some of the previous ionization technologies did have a risk of ozone, and you want to make sure that you're using this UL2998, that it has to meet that, because that has the limits on how much ozone. If it doesn't have that, do not use it. But basically the bipolar ionization, so it's going to basically charge both negative, some of the particles negative and some of the particles positive. So it's doing both poles basically. And when you do that, what's going to happen is the different particles, you're going to have negatively charged ones and positively charged ones. So they're going to start clumping together. So as you do that, you're going to get bigger and bigger clumps of stuff. So you got two things that are happening here. One, you're going to cluster these things together. So now when it goes to the filter, they're a lot bigger items. So they're going to much more effectively get captured in the filter. The other thing that happens is it disrupts the surface proteins and keeps it from reproducing and makes it inactive that way. So these are kind of the two things we're looking at. And the benefit here is there's lots of different styles that you can do here. This happens to be just one manufacturer's product line. On our bigger coils, you're going to have this lined up item. So you're going to have several rows of them in our bigger units. If we had like a 5-ton unit, I might just have this. We had a couple of our senior engineers purchase this for about $500 from the manufacturer, then drop it in their units themselves, like a 5-ton unit. So it's kind of a practical way to go. If you've got like a VRF or a fan coil or a PTAC unit or something like that, you might use this little ribbon style. So that's kind of some options. So, places where we might not have been able to do UV, we can get bipolar and get it installed. So that's kind of where we've pushed. We always start with the UV, and our fallback is our bipolar ionization. The differences here on the UV, we're going to be changing our lamps out every couple of years. On the bipolar ionization, you're going to change out the whole item in 5 or 10 years. So, you got lamps and ballasts on the UV. Here, you're going to change out the whole fixture. Our install costs are less, between 40 and 70 cents a square foot. Again, we talked about being more flexible, and you can put it places where the ASHRAE is saying the same thing, the CDC. So, look at the studies and things like that. The other thing about bipolar ionization, so we were talking about contaminants of concern earlier. We have utilized bipolar ionization, and if you've got, there's a couple options on ventilation. So most ventilation you do 5 CFM a person and 0.06 CFM a square foot is what most of the code requires in most of our spaces. We end up with different conference centers or things like that where the base building system just can't handle that amount of outdoor air. Well, you can go through either like a charcoal filter where you just clean the air, or the bipolar ionization will do the same thing. So what's nice about bipolar ionization is it'll take out VOCs, it'll take out the other contaminants of concern, things like that. It actually cleans the air, takes out the odors out of the air. So where the UV is just killing off items, this does other, takes care of VOCs and smells and other contaminants of concern. So that's what's beneficial here. So now we can bring those other contaminants of concern down. It's not really addressing the CO2, but it's handling, again, the CO2 is not actually the risk. It's these other contaminants that the CO2 is representing in the measurements. So this is something you can use for reducing outdoor air, kind of your more dense spaces or handling smells or things like that. Questions on, I don't think I saw a chat thing pop up at all. Any questions on bipolar? How we doing on time?
Nothing yet, Dave.
Okay, so we'll just hit humidity control really quick and then we'll wrap up. So those were the three things we wanted to do, right? We wanted to do the outdoor air, we wanted to do our filters, and then we went to, our next step, which is a little more involved, obviously, was air sanitization. But we want to touch on humidity control because obviously it was an issue that's been definitely presented. So the goal here is to provide, unfavorable conditions. If everyone remembers back during the fall, it was predicted, okay, cases of COVID-19 are going to go up in the winter, and the reasons are more people are inside, but the bigger reason is the lower humidity inside. So in our market, if it's, it's not uncommon to have a relative humidity indoors during the winter at 15 or 20%. And really the thing that we need to look at is two things are happening. One, if we remember back to our first chart here, those droplets are evaporating. And if it's, 15 or 20% relative humidity inside, they're going to evaporate much quicker, in that than it's going to be at 50 or 60% relative humidity. So we have many more virus particles stay airborne than are going to fall out of the air. So that's the biggest issue we have going on. So we have many more virus particles floating around in the air. The other thing to look at is on the people side, right? So the cilia hairs in your airways, when the humidity is higher, they're much more flexible and they can shed the pathogens easier. When the air dries out, they become stiff and they don't bend and they don't shed the pathogens. So you're much more susceptible to pathogens when the humidity is low. So those are the two things that are going on. So you got more people inside, but much more virus particles going on, and then your body's not as adept at shedding those pathogens. The issue is it's very costly to add humidity into our system. So all that outdoor air we're bringing in that's drying out our space, basically to push it back up, we've got to take gallons and gallons and gallons of water and basically do a phase change. So I got to take that gallon of water and I essentially got to boil it. So the amount of energy to boil it is how much energy I got to put in. So that's a lot of money we're going to spend. We got to deal with all the stuff that was in the water. So if, we either have to treat the water or we got to deal with it going down and being a dust on our stuff, or the dust inside the, that ends up after we do this. So you have those solids you have to deal with. So typically over the years, we've put them in, in hospitals, data centers, processing, things where we have to have that humidity for other reasons, but we've not put it in standard offices, not done it in schools, not done in other spaces like that. It's very cost prohibitive. We might start adding it for higher risk, senior centers or things like that. But we don't think this is going to be the common approach that's going to be implemented throughout. We believe some of the other things will be come in place long before humidity control does, just because of the cost and how much you have to go through to get there. So if we summarize, we want to address all three transmission methods. We're going to be looking at outdoor air and filtering first. These are easy steps we can do. You just have to be motivated to go do them, right? So you have to spend a little bit of time, a little bit of money to figure out what you need to do, put them into effect, and then it brings those numbers down a lot. Then you want to look at air sanitization, which way you're going to go. It gives you opportunities to reduce that energy consumption on that outdoor air. It does take, you got to get the products in hand. The bipolar tends to have a shorter lead time than the Uvgi. We'll say that based on what we've seen. But it's a great long-term solution. And you got to look at your individual building and systems and figure out the specific solutions. There are other things, pressure relationships or different things like that you might want to look at in terms of a multifamily thing or a school. What are you going to do when you send sick kids down? So there's other HVAC things that you have to approach. And you got to find the specific recommendations, and you have to look at what can my system handle. It's not a one size fits all. Hey, I sat through the seminar. It says bump our outdoor air to 30% and put a MERV 13 filter in there. You put too big of a filter in that your system can't handle, it's going to choke down that ventilation, which was your first step, and it could possibly, worst case, it could shut off your unit on high head pressure. So you got to kind of go through, work it through, figure out where you can get your better contractors can do some of this, or get some engineers or something like that on board. So that's kind of our thing. I think I saw the chat pop up here. Any questions? Are Bill and Zach retired? So Bill is retired. Bill lives in, for anyone who knows, is Bill Allen. So it's Bill Allen, Zach Sharif are the two partners. Bill's retired. He's down in Tampa. He's also got a place in the Keys. He was driving what's called the conch train down there when he first retired. So he was doing the tour guide on the conch train, tram tours in town. Zach is not retired. Zach is giving us a rolling 7 years of, Zach loves the work. We'll see if he ever retires. But anyway, what else we got here? Anything else? All right, I think that was it.
That was great, Dave. Thank you so much for sharing that. I was curious, I had one question. I know we're running a little bit over, but if people have like one more minute to stick around. With new construction or new ground up systems that you're designing, are these still like the approaches, or is there anything else that comes into play?
It's still the approaches. Like I said, one or two of the buildings, it has been, okay, do you want to do air versus water side? I don't know that's really steered that system. We are, bipolar seems to be landing in more of our projects than the UV. We do seem to be implementing that. We're actually looking at animal shelter now that we're actually talking about putting bipolar in there because of, the dogs getting sick and keep, kennel cough and stuff like that. So it's started to push the issue in some of the other ones. And the filter rates we're seeing, definitely the MERV 13s are kind of the more standard thing now from Go, that all our systems we're designing can handle MERV 13. So we are starting to see that come into play a little bit in terms of our systems. And I think there's going to be, the standard of care is going to change. What the industry does as the norm is going to change, and you're going to have to kind of implement some of these just because that's what's being done. And I do think some of the codes will evolve a little bit, as we go forward.
Okay, great.
By all means, if anyone wants us to present this to any other groups they have, I think we're up to like 1,300 people or so we've done it for now. I forget, 70 times or something like that. But we've been give it to whatever group, whatever clients you might have at school system or anybody that you think might benefit from it. The push has been a little less of late, but still we're out here if anyone has needs us to present it for them.
Perfect. And we will definitely share those slides. So if anybody wants to pass those along, we'll have those posted on the BEC Baltimore website. All right. Well, thanks everyone for joining. Again, our next event will be on May 18th, and we'll be sending out some information about that shortly. In the meantime, if you want to contact us, our email address is info@bec-baltimore.org. So we'll see you then. See you in May. Thank you.